Hello and welcome back to today's video. In this video, we're going to investigate the main reason of why we're interested in continuous functions at all. And briefly, that reason is that we can optimize properly over continuous functions because continuous functions will assume their maximum and minimum provided they are defined on a reasonable interval, and reasonable means closed and bounded. We'll get to the details in just a minute, but first we need to define what we actually mean by a minimum and a maximum. So this section is titled Minima and Maxima of Continuous Functions. And as I said, the first thing we need to do is we need to properly define a notion of minima and maxima. So for that purpose, let D, the domain, be some subset of R, and let F be a function defined on D with a codomain of R. Then we'll say a point, let's call it X star, in D is called a maximizer, or more precisely a global maximizer, but we'll usually omit global if it's clear what we mean. Of the function f in D, and again we'll usually omit in D if we just refer to the complete domain. So point is a global maximizer if f of x star is greater or equal to f of x for all x in D. So the function value at this point x star is the highest possible function value over the whole domain. Of course, there may be more than just one maximizer, and it's not even clear whether there is a maximizer or not. There are functions that don't have a maximizer. The corresponding function value is then referred to as a global maximum of f in D. And again, we'll omit global, and we might omit in D if it's clear from the context what we refer to here. Point 2, of course, we can also define a global minimizer, and the definition is pretty much the same. So a point x star in D is called a possibly global minimizer of f in D. And now the condition is if f of x star is less or equal to f of x for all x in D. And again, the corresponding function value is called a global minimum. And finally, let's add one more notion to this definition. Point 3. We call a function bounded if there is a constant, finite constant, such that the absolute value of the function values never exceeds that constant. And we call it bounded below and bounded above if there is a constant that bounds the function values below and or above. So this is the last point here. The function f is called, let's start with bounded below. If there is some constant, we call it b underline in R, such that f of x is always greater or equal to this b underline for all x in the domain. Similarly, it is called bounded above if there is some constant, we call it b overline in R, with f of x is less or equal to this b overline for all x in D. And finally, the function is called bounded if it is both bounded below and bounded above. So a function that is both bounded below and bounded above is simply called bounded. So of course, a function that has a global maximum and a global minimum will also be bounded. Some quick examples here. We're just going to show you some graphs for these. So for example, let's say we have a function that looks like this here. We can see this function is obviously bounded above. This is one possible b overline, so this is bounded above. It's not bounded below because it extends in this direction indefinitely. It does have a global maximum. That global maximum would be here. And in this case, it's even unique. And this here is the maximizer. So this is a maximizer. This is a global maximum. This here refers to the function being bounded above. And it's not bounded below. And it does not have a global minimum. Let's have a look at one more example. Say we have a function that looks like this here. Then this function is not bounded, right? Again, because it extends indefinitely in this and in that direction. It does not have a global minimum and it does not have a global maximum either, simply because it's not bounded. Please note that these points are not global maxima or minima. Those would be local maxima, minima, and we would investigate those later. But this is a function that does not have any maximizers or minimizers on a global scale. Right? So not bounded. no minimizer, and also no maximizer. And finally, let's have a look at one more function, one that is bounded but does not have maximizers or minimizers. So let's say we have a function that looks like this here. Right, so we have asymptotical behavior here. Right, in particular, this here is an asymptote, and this here is also an asymptote. So this function is bounded. It has bounds above and below, but it does not have a global maximizer or minimizer because it can become arbitrarily close to these asymptotes here. And there's no point where we can say it doesn't get larger or it doesn't get smaller than that. So this function does not possess minimizers or maximizers. No minimizer, no maximizer either. Now let's get to the central theorem of this section. You will have noticed that the functions that I sketched here are all continuous functions, right? There's no discontinuities there. The problem with these is the domain of these functions is R. And what we need in addition to continuity is a domain of a specific kind. We need an interval that is closed, so a closed and bounded interval for a function to assume its minimum and its maximum. And that is what this next theorem tells us. So here's the central theorem about continuous functions, basically. Let A and B be in R with A less than B, and let F be a function defined on the closed and bounded interval from A to B with a codomain of R, and F is a continuous function, so let that be a continuous function over the closed and bounded interval A, B. Then this function f is bounded and it attains its minimum and maximum over the interval AB. And what that means is, in particular, there are points x min and x max where these minima and maxima are attained. And there may be more than one, of course. Right? So the minimum or maximum does not have to be unique. There may be multiple points. So possibly multiple points x min, x max. The important thing is there exists at least one of each of those in the interval AB, such that where x min is a minimizer, that means f of x min is less or equal to f of x for all x in the domain, and f max is a maximizer, so that's greater or equal to f of x for all x in this interval between A and B. And just as a quick remark on terminology, a closed and bounded interval is also called a compact interval. So compact means closed and bounded. And we use this from now on to simplify notation a little bit. There's one more theorem that is a little more general, and that is called the intermediate value theorem. The idea is similar to that, so I'll list it in this section as well. The main idea of that theorem is to say if a function assumes certain values and if that function is continuous, and again we have a compact interval as its domain, then every possible value in between those two that we know of has to be assumed by the function as well. And that's the intermediate value theorem because it says the function attains all intermediate values if we have some known function values already. So as before, let f a b to r be a continuous function on a compact interval AB, so closed and bounded. Then for every value of gamma, any constant that is between the minimum and the maximum function value. So any gamma in R with minimum of f of x over the domain x in AB less or equal to gamma less or equal to the maximum. So we know that f attains these two values, and then we can take any value in between. And the theorem says there is a point where this value is actually attained. So for every gamma that is in between minimum and maximum, there is a point x star in AB with f of x star equals gamma. So basically, if we know the minimum and the maximum of a continuous function, then we know the image of that function. For non-continuous functions, that may not be the case. Okay, so in other words, f attains all intermediate values between minimum and maximum. And that theorem also gives us a little insight into the image. I already said if we know minimum and maximum, then we know the image. And of course, what we also know is that the image is then also an interval. The minimum and the maximum are actually assumed as function values, so they will be included in the image, and there will be the boundaries. So that means the image of a continuous function on a compact interval is again a compact interval. It's again closed and bounded. So the image of a continuous function on a compact interval is again a compact interval. So this is, as I said, probably the most central point that we need to make concerning continuous functions. Of course, they are extremely important in some other applications as well, but for us, the main importance of continuous functions lies in the fact that they assume their minimum and their maximum and all intermediate values over any compact interval. And one possibility to make use of that is to determine numerically an approximation to roots of continuous functions. And we do just that in one of our upcoming videos. I'll see you then.